Okay, sorry about that. I'm Anjali. I'm excited to talk to you today about rule inference for equality saturation applications. So first, jumping right in, I'm not going to do a big background on equality saturation, but the very basics that you need to know to understand the rest of this talk are just that equality saturation is a technique that uses this data structure called an E-graph, and it constructively applies a set of rewrite rules to compactly represent lots of equivalences simultaneously. But equality, and it runs this until saturation, or more realistically, until it hits some kind of resource limit, like a time limit. And equality saturation is everywhere. There's lots of recent papers that are doing interesting things with EXAT for different applications. But equality saturation is only as powerful as the rules that you use. And writing rewrite rules by hand is really hard. It's time consuming, it takes a lot of engineering effort. It's difficult to validate the rules, which compounds the fact that a single unsound rule can compromise the soundness of your whole system. And it's difficult to debug the rules, both the rules themselves and also the performance of the rule set in your tool. So because of this, there's been some work recently in trying to learn these rules automatically. So here are just some recent papers on automated theory exploration and rule inference. But despite all of this recent work, building and maintaining rule sets still requires significant engineering time and effort. So we hypothesize that traditional theory exploration is too inflexible. We propose programmable theory exploration implemented with the Anumo DSL, which we'll talk about in a little bit. And we'll show that this scales better and enables new strategies for rule inference. So that's kind of outline of what I'll talk about today. But diving right in, so traditional theory exploration typically follows this three-step pipeline, where first you enumerate terms from the domain, then you find rule candidates, which naively would be the full cross product of your enumerated terms, but these traditional theory explorers have kind of clever techniques for finding rule candidates, usually by sampling from the domain. And then finally, you need to select a subset of your rules from the rule candidates that are sound and that are minimal in some sense. And so users of traditional theory explorers are usually expected to provide these three inputs: a grammar, an interpreter, and a rule validator. The grammar tells you how to enumerate terms from your domain. The interpreter tells you how to evaluate those terms on concrete values, which is used for the candidate generation that I mentioned. And then the rule validator tells you whether the rules that you find are sound. So given these three inputs, you run through the theory exploration pipeline, and you get out a rule set. So sounds great, right? But the problem is that it's not modifiable. It's a pretty one-shot push-button approach, and so it's not easy to make changes if it doesn't do exactly what you expect it to do. Also, the candidate generation and rule selection steps typically have hard-coded resource limits, which can be a problem in practice. And term enumeration doesn't scale, and usually these traditional theory explorers do exhaustive enumeration, and it's pretty difficult to encode other enumeration strategies into the tools. Also, you need an interpreter. If you can't implement an interpreter for your domain, you simply cannot use these traditional theory exploration techniques. So now I'll talk a little bit about how we solve some of these problems by using a DSL. So the first thing that I want to talk about is we can kind of all agree that the term on the left is less likely to lead to an interesting rewrite rule than the term on the right, and we just sort of have this intuition. So our insight is that users have intuition about what parts of the domain are worth exploring, but existing tools don't give you an easy way to leverage that. So what we're going to do here is we're going to turn the theory explorer inside out, and we're going to expose a small set of useful operators for rule inference, and the best way to look at that is just by examples. So the basic data type in Anumo is called a workload. You can think of it just as a list of terms. So here we just have literals from some domain. You can also use a workload to represent a grammar. So anywhere you see all capitals, you can think of that as a non-terminal from some grammar. And then you can compose workloads together. So here we're going to plug expers into itself, and let's take a look at what the plug operator does. So it takes two workloads and a string, and it's going to give you all of the combinations of replacing that string in a term from W1 with a term from W2. So an example here, the first term, X, there's two ways of replacing that with a term from W2, right? You get 1 and you get Y. And then the second term, foo XX, again, we're going to replace the X anywhere we can with a term from W2. And so you can see we get this kind of like cross product of terms from W2 in the expression from W1. So using the plug operator, you can easily construct these kind of patterns of terms, right? So if we plug the literals into the products workload, we're going to get all of the ways of multiplying two of these atoms. And then if we plug that workload that we just constructed into sums, we'll get all of the ways of making a sum of products from this domain. So you can see how you can use the plug operator to kind of incrementally compose and construct these workloads that target parts of your domain. So going back to this example from the grammar, if we plug expers into itself and then plug in the literals at the leaf nodes, what we're going to get is terms up to depth 2 from this grammar. So you can easily use plug to do exhaustive depth first enumeration. But remember, our goal here is to actually infer rules, right? So what we've done so far basically covers the term enumeration step of traditional theory exploration. And then Anumo also has operators to find candidates and to select rules. And then we can also filter workloads. So here we're going to plug E2 into E1. That looks something like this. And then we'll filter by size 4. So we'll filter out all of these terms. But you can see that the last term in E2, 4 plus 5 plus 6, is already itself bigger than our size filter. So what we actually might want to do is filter on E2 first, and then plug that in and filter for size 4 there, so that we don't have to expand out the full plug and then filter it all the way down. So it turns out this optimization is super important because plug also grows exponentially, so it's important to keep the size under control where we can. And this is just stated a little more formally that you can, a filter of a plug is the same as filtering the plug if you also filter on W2 first. But for this to be valid, you need F to be a monotonic filter, which just means that for every term that satisfies the filter, every subterm also satisfies the filter. So here's a couple of examples. Excludes is monotonic, contains is not, right? Because you have this subterm that doesn't satisfy the filter even though the full term does. Okay, so that's a really fast overview of the Anumo DSL. Now let's see how it actually works in practice to find rules. The first thing we did is we compared to Ruler, which is an existing tool for theory exploration, and we find that pretty short Anumo programs are able to find rule sets that are strictly more powerful than rulers. So the second to last column, this column in green, is showing that Anumo's rules can derive all of the rules found by Ruler, while the last column is showing that the reverse is not true. Ruler's rules cannot derive all of the ones that we find with Anumo. Please look at the paper for more about derivability. I'm not really going to get into it in this talk, but the very high level is that more rules are not always better, and we give some definitions and metrics for how to measure proving power of a rule set. Next, we wanted to see how Anumo scaled to large grammars, because we know that can be a bottleneck for traditional theory explorers. So we were inspired by the halide domain, mostly just because it's a pretty big grammar. So we scraped out 725 rules from halide, and we tried to learn them with Anumo. The first thing we did is exhaustively enumerated up to a size bound. And since this grammar is pretty big, we time out after size 5. So we can learn rules that derive 42% of halide's rules up to size 5 in this grammar, and then with traditional techniques, you'd be kind of stuck at this point. But since Anumo has these like composable operators that make it easy for domain experts to leverage their intuition, we can kind of see that, like, okay, we know which operators here are closely related and so are more likely to lead to interesting rewrite rules. So what we did is we constructed an Anumo program to first enumerate just the Boolean operators and learn rules there. Then we enumerate just the rational operators and learn rules there. And again, for the predicates. We can compose these all together, but we also know that there's going to be some rules that use overlaps of these operators. So then we can write some custom workloads, again using Anumo, and put it all together with an Anumo program that is just 140 lines, so it's not very long or hard to write. And as a result, we learn 845 rules that are capable of deriving 90% of halide's rules. And the point here is just that with guided search and with these composable workload and rule set operators, you're able to make progress past the point of exponential blowup, which is unlike traditional theory explorers where you're just kind of stuck as soon as things blow up too much. Anumo also enables entirely new strategies for rule inference. One of them is called fast forwarding, which is a phased approach for finding shortcut rules. It's pretty short. We implemented it in less than 10 lines of Anumo code. And the really exciting thing about this algorithm is that it doesn't require an interpreter. Here's what the algorithm looks like. I'm not really going to go through it in detail, but happy to talk about it more later. Instead, I'm just going to talk about an example. So Herbie is a tool that uses equality saturation to reduce error in floating point expressions using rewrite rules over numerics. This rule you might be able to learn with traditional techniques. This rule you can't, because equality is not decidable for the real, so you're not going to be able to write that interpreter. Now, you might be able to rewrite your sine and cosine in terms of complex numbers and then apply rewriting over those terms. But this is unlikely to scale due to resource limits. So what we do with the fast-forwarding algorithm is we start from an initial set of rules, and we strategically grow and shrink the E-graph, and then we extract rule candidates from the things that merge so that we can find shortcuts through the rule set to improve the results under resource limits. And here are some of the examples of rules that we actually find with fast-forwarding. We have trig, we have exponentials, we also have CAD models. None of these are domains that are supported by existing tools. To measure the effectiveness of these rules, we plugged our rules into Herbie, the tool for rewriting floating point that I mentioned. All the way on the left here, we have the expert written rules. All the way on the right, we have the prior state, the art of inferred rules. And we show that Anumo is, while we're still a little behind the expert written, we've made a lot of progress compared to prior inferred rules. We also measured the effectiveness of Anumo's synthesized rules in the 3D CAD domain by using this tool called Selinsky that does equality saturation to shrink ASTs for 3D CAD models. And we find that the Anumo synthesized rules nearly match the performance of handwritten rules for that domain. Last thing I'll talk about is porting rules across domains. So for BV4, it's pretty fast and easy to synthesize rules, while for larger bit vectors, it's quite a bit slower. So what we did is we wrote an Anumo program that can synthesize rules for BV4, and then we cast and revalidate those for BV128. And basically, we find that the ported rules have almost as much proving power at a fraction of the cost compared to directly synthesizing for the domain. That's just about all I have. Ryan, Tjoa, our amazing undergrad, also had a poster, so please talk to him as well, especially about that Selinsky case study. And I'm happy to take any questions.
Hi, great talk. So I have a question. So if I were to try to solve this problem, like what you showed at the beginning where you said, I think you agree that this rule is more natural than this other one. Mm-hmm. And the point of naturalness is that, like, if you had a model of what languages look like, the ones that you're extracting rules for, you could target yourself towards most likely patterns rather than just patterns that never appear in practice. Like that not, you will never find that in a language. So you shouldn't experiment. And so there is a little bit of work on, I wonder basically if you can learn a model, think of it as like a probabilistic grammar of what programs look like. So if I had such a grammar, one that says not is very unlikely, then can your language capture this probabilistic approach? Basically say only explore, instead of depth first up to 4, explore the most likely terms according to some probability distribution. Like, is your language already ready to do that?
Yes, we don't already support probabilistic enumeration, though it's a really interesting idea and I think would probably not be too difficult to add. We also can support, like if you have a real workload of terms from some like actual like application, you can make an Anumo workload out of those.
To make it easier, instead of probabilities, I can take the negative log and then just say not just cost a lot, cost like 10. Then can you already do?
Not in the enumeration. You can include that in the cost model for extracting rules and say, like, I don't want to extract a rule that has like more than 3 negations or something like that.
Cool. Yeah. Thank you so much.
Yeah, thanks.
So yeah, thanks for the wonderful talk. So if I understand correctly, your DSL outlines a space for exploration, but if you find a rule in this space, how do you know if the rule holds or not?
Oh, so the user of the domain will provide a rule validator that will check the soundness of the rule. And so when we find and minimize, give you like a minimized set of rule sets, they're sound up to the soundness of the verifier that the user provides.
What validator do you use in your evaluation?
So most of the domains that we've implemented, we encode to SMT for the validator. Yep.
Okay, thank you.